Hey guys, Lainey here, and today we're at Eskimo Cold Storage Facility. Eskimo is actually a freezer storage facility, and it's a perfect example of how foundation engineering is found in the real world. Cold storage buildings place unique demands on their foundation design due to the combination of heavy structural loads, strict temperature control, and very tight settlement tolerances. So even though we're standing here looking at a finished structure, there's a lot happening beneath this building that most people never think about. Before I get into specific foundation elements, it's important to understand why freezer buildings are built different. Inside the facility, the temperature is kept well below freezing. That means the slab and the soil beneath it are constantly exposed to extreme temperature gradients. If the subgrade ever freezes, the water in the soil expands and causes frost heave, which can lift the slab, damage racking systems, misalign doors, and disrupt operations. On top of that, these buildings carry heavy loads from pallet racks, forklifts, and high elevations. The foundation system must be strong, stable, and well controlled. One of the main foundation elements here is the continuous footing system. These run along the perimeter walls as well as some of the interior walls. These continuous footings distribute loads evenly along long stretches of wall, which is important for a building like this with extremely tall, insulated metal panels and CMU walls that need stable support. Next are the spread footings, which support a concentrated load from the columns. These footings vary in size throughout the project, depending on dead, live, wind, and seismic loads acting on the column and range from a 4-foot square all the way to an 8-foot square. This project also uses reinforced concrete piers beneath many of the columns. The main purpose of these piers is to be able to reach frost depth with the footings. You might look at this drawing and think, Laney, there's no way the frost depth in Georgia is 5 feet 6 inches. And you'd be exactly right. In this project, the site paving sloped down by 4 feet at the loading dock area. So, yes, the total pier height is actually 5 feet 6 inches, but in reality, the top of footing is only 1 foot 6 below the site paving. This is why coordination is extremely important in large projects like this. Looking at a geotechnical report for this job site would tell you the specific frost depth required, which is where the 1 foot 6 came from. Coordinating with the civil engineer would allow you to confirm that that final grade or final site paving may vary from your finished floor elevation, causing you to adjust your foundation design. This project also has many retaining walls. These walls are required due to a drastic elevation difference between finished floor and site paving. This retaining wall provides somewhere for the IMP and slab to bear on, but also retains the soil underneath the slab. You can see how the footing isn't centered with the wall, and you might think, Laney, what engineer designed a footing that is eccentrically loaded? Since this is a retaining wall, the wall not being centered on the footing helps us in preventing the wall and footing from overturning. With all the soil pressure acting laterally on the wall, this causes the top of the wall to want to rotate. In order to counteract this movement, the larger side of the footing uses the weight of the soil sitting on top of it to push back against that rotation. By extending the footing on the heel side, we create a longer lever arm and more resisting moment to keep the wall from overturning. Now let's talk about the slab, because in a freezer building, the slab is one of the most critical components. The drawings show a 9-inch thick slab with a special shrinkage compensating concrete mix, reinforced with macro synthetic fibers in lieu of steel rebar. The slab is also placed on top of 6 inches of insulation, a 10 mil vapor barrier, and a 3-inch mud slab. But one of the most important features is the network of tubes that run through the entire underside of the slab. These tubes constantly circulate warm glycol to keep the soil beneath the building from freezing. This helps eliminate frost heave, reduces potential cracking in the slab, and reduces the number of freeze-thaw cycles it must encounter, which will allow the slab to have a longer life cycle. So even though this looks like a normal building from the outside, the foundation system underneath is doing a lot of work. Continuous footings, spread footings, combined footings, piers, temperature-controlled slabs, and retaining walls are essential in keeping Eskimo cold storage a safe place to work. This is a great example of how foundation engineering shows up in everyday life and how geotechnical, civil, and structural design comes together to solve real world problems. Thanks for watching!